Gita's like, shift, but do not cross the streams, please.
We should be live again. Thankfully, it wasn't a long walk. Do not cross streams.
Everyone needs a good Ghostbusters reference.
Hey, people found it, and we're live again. We'll go for like 5 minutes, and then we'll bust right into this next episode, and then we'll stick around. We'll answer your questions for a little while. So is that why we're doing this, by the way? Because you have this convention that you're going to next week, later this week?
I have back-to-back meetings, so and they're of course on opposite coasts. So Wednesday I'm flying out to Baltimore for a meeting on multi-messenger astronomy communications at Space Telescope. And then I'm turning around, getting home from that on Saturday, and then flying Sunday to San Francisco to go to QCon, where I'm giving a talk on Wednesday that was originally a talk on Monday, which is why the quick turnaround. And yes,
Thought you were
yes,
going to
this is
travel less.
I'm doing 1 week a month instead of 3 days a week.
Oh, that's not bad. That's bad. That's an improvement. All right. So if you're wondering what it is that you have stumbled into, this is the second live episode of Astronomy Cast that we are going to be recording today. This is episode 546, Weird Issues, Planetary Migration. Are we almost out of Weird Issues episodes? Is this series going to continue?
I don't know yet.
I mean, I could probably think of more weird issues if, I think,
I'm enjoying it.
Yeah, well, I mean, I think what I like about it, right, is that it's like both of us, I think, have been doing this job long enough that we have a much more nuanced understanding of the state of the current planetary science and physics and stuff. And so we can smell the disagreements, the controversy,
Yes.
and we can then just sort of live in that controversy for an episode, which I think is kind of fun because
Yeah.
it's just what we thought used to be very simple. And even like things like what killed the dinosaurs, how did the moon form? Like a lot of these things used to be fairly cut and dry and now have a lot of nuance in them,
Yeah.
So it's I'm sure we can think of more of them if people are into them.
And it's really just kind of startling how much that we thought were solved problems are absolutely not solved problems.
Yeah, absolutely. That is the part that I enjoy is like even planet star systems, right? So you say like what are there, for the longest time we would say that multi-star systems were the most common in the galaxy.
Yeah.
But they're not. That in fact, multi-star systems are the most common in non-red dwarf star systems.
Right.
But most stars are red dwarfs, and most red dwarfs are singletons. And so, in fact,
are so biased by size.
Yeah, I know. And so, in fact, the vast majority of star systems in the Milky Way are single stars, not multi-stars. So, which is, I guess, more good news for the prospects of, I don't know, life, planets. I'm not sure, because multiple star systems can be mayhem for planets. But anyway,
I think red dwarfs are more chaos to planets than multi-star systems.
And they're no picnic to be in a planet orbiting a red dwarf star, for sure.
No.
All right. Are you ready?
Yes. Yes, I am. I have pressed record and it is recording.
Perfect. I have also pressed record and also can confirm is recording. All right. Let me get my intro. Now, Right. Here we go. Astronomy Cast, episode 546. Weird Issues. Planetary Migration. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
Great. For anyone listening, it's been a week since you've heard our dulcet tones, but for us, it's been scarcely 10 minutes. So here we are with our next episode on our Weird Weird Issue series, and what Pamela is traveling, so we had to bunch them up. But I don't think the science will change dramatically in a week or so. But could be wrong.
It's true.
Yeah.
It's true.
Now, before we discovered other planets, our solar system seemed like a perfectly reasonable template for everywhere. But now we see massive planets close to the stars, which leads you to the question, how does it all get there? Do the planets form in place, or do they migrate around? All right, Pamela, you put this in the docket. You had a much more complicated title when you originally put this in. It was something to the gist of which I just put as that last sentence. Did everything form in place, or did it all migrate around?
I'm not allowed to name things. I am an astronomer.
Yeah.
The one precludes the other.
Yeah.
We've discussed this
Yeah.
before. You are here to name things.
You are either too poetic or
Wordy.
too wordy.
Let's
yeah.
just go with wordy.
Yeah. Yeah. And I'm all about the clickbait, man. So keep it short. But no. um, so again, as always, each time we kind of go back and think about the days of yore, and what did we think about planetary formation and the locations of the planets back in old-timey land?
Well, back when we only had one solar system to study in detail.
Right, there was only one.
we came up with this beautiful solar nebula model, which the big pieces are still generally thought to be true, but the details, oh my goodness, were wrong. So the picture that we had before is that solar systems form and the light pressure of the sun pushes most of the gases outward, leaving rocky worlds forming internal. The gas gets gathered up, forms usually one giant gas giant. Outer in the outer solar system, you can end up with some ice giants, maybe a smaller gas giant, and things form in a nice and ordered way. And you may end up with resonances between those massive worlds that push things out further and send rocks cascading in. But in general, where we see things is where they formed, which means that when we look at things like the asteroid belt, which is located at that place in the solar system where the heat from the sun either baked things dry or left them moist, um, those asteroids that formed there are still representative of that solar nebula and the distribution of material within it. That's what we thought.
Right. And in fact, the distribution, like I forget the exact rules on this, but if you looked at the locations of all of the planets in the solar system, there was a really straightforward, almost mathematical position to each one of the planets, as long as you assume the asteroid belt is a planet.
It was a beautiful set of ratios.
Right, there was a beautiful
that led
set of
people
ratios.
to think that that was where they had to be.
Yes. And so we
It's
assumed
not.
that everywhere we looked, we would see the exact same thing. Did we?
No.
What did we find?
So one of the first things that we found was gas giants don't always exist far away from their stars. They tend to be found snuggled up next to their stars periodically. And we'd also assumed that they'd have to be in circular orbits because angular momentum issues. But then we find them in these highly elliptical orbits. And And we assumed that there would only be one gas giant, truly giant Jupiter like planet per star. And we sometimes find more than one. And so basically all the rules we came up with were wrong.
Right. Yeah. And so now, if we were to look out into the universe and try to make some rules about how planets, where you'll find planets in other star systems, what are the rules?
I think that depends on who you talk to and what they ate for breakfast that day.
So
It's
is it bordering on no rules?
it's it's bordering on new rules appear to come out every week.
Right. But
And
there are no, like, there have been star systems found with, as you mentioned, giant planets orbiting close to their stars, multiple giant planets, planets that are small, located close, in between, planets around red dwarfs. It's a mess. There are it's chaos out there.
if a solar system could do something, it has done something.
Right.
And and this is kind of awesome. And what's fun is watching the theorists play catch up. And one one of my favorite examples
Poor
of this,
theorists.
I know. So
Yeah.
so yes,
Yeah.
one of my favorite examples of this is a new paper that came out in the Astrophysical Journal that I had as lead author graduate student Renata Ferleek, and this young woman did this amazing work where she ran a myriad of hundreds of simulations of solar systems where she started out each solar system with 10 worlds. And she started out each solar system with a different amount of mass and let the mass fall as it would to the different planets. And she allowed her models to have multiple massive gas giants. And this was new. Like, this wasn't a thing people had been doing before because solar systems are not supposed to have multiple massive gas giants.
Don't we
And
have two?
well, Saturn's not that big.
Oh, okay.
So they're allowing two Jupiter or
Two
larger
Jupiters, okay,
side.
or more. Right.
Yeah.
Okay.
And and so the the models that she did were able to explain all of these crazy Jupiters we're finding as what happens when you allow a solar system to evolve for 20 million years and notice that worlds collide. And and the fact that worlds collide seems to be something that we have to keep realizing. And this is one of my favorite things as someone who does not do this research, to sit back and watch as a spectator. Because first there was this realization of, oh, expletive. One of the best ways to get at the Earth having a moon is to assume that a Mars sized object hit the proto Earth. They collided, they splashed up the light materials recoalesced. We ended up with a moon that's lower density than the Earth.
Right.
We even named the prior object Theia.
Right. And so, like, I'm just imagining the cognitive dissonance here, right? You're saying planets don't move, but also a planet moved and crashed into the Earth, but also planets don't move, except for that time that they did, which they don't.
Right, right.
Right.
And so the fact that other collisions may have occurred, people talk about, especially when we look at things like Uranus, which has its pole pointed into the plane of the sun. When we look at Venus, which seems to be flipped all the way over, well, maybe that could have occurred via some sort of a collision. But there's always that modeler out there trying to figure out how to do this using nothing more than tidal forces so that no collisions are required, because we keep assuming that collisions have to be rare. But then there was a recent paper that was able to explain that the reason Jupiter isn't as dense in the core as we had previously expected, as measured from its angular moment of inertia, is it appears that Jupiter got smacked by a massive protoplanet many times the size of our Earth when it was young. So we now have in our solar system alone Earth Moon, result of a collision, Jupiter's fluffy core, and they did use the word fluffy to
Right.
describe this, explained with a massive collision,
A super Earth.
a super
Yeah.
Earth.
We used to have a super Earth, and then Jupiter ate it.
Or it committed suicide.
Yeah.
I don't know who was on the elliptical orbit that drove this collision.
Right. So so then, I mean, this idea then that a planet crashed into the Earth, a planet was gobbled up by Jupiter or through itself into Jupiter.
Into Jupiter.
Uranus is flipped over on its side and is in the wrong position in the orbit compared to Neptune in the solar system. It looks like they've been flipped. This started to lead astronomers to the possibility that in fact maybe planets shift around. Maybe they do shift around in a solar system.
And once you start thinking about that, you start looking at the data in a completely different way. So initially, when we were trying to figure out how the heck do you get a Jupiter snuggled in next to its sun, everyone was blaming frictional effects, drag effects. The early Jupiter was inside the disk of material, the protoplanetary disk, and it kept consuming things at smaller and smaller orbits until it had migrated in to where there was the hollow spot in the disk, and it stopped there. Well, now, by instead looking at this as, oh no, it simply got smacked around through collisions with other objects and got pushed in. Perhaps it ended up on a highly elliptical orbit, and highly elliptical orbits do over time get tidally made more circular. Um, this is a completely different and, in many ways, easier way to explain what we see. And tidal forces do still play a role. Don't get me wrong. This is how things like when you look at Mars, its inner moon Deimos will eventually become its inner broken band of rocky rubble.
Oh,
Deimos,
Phobos.
Phobos.
Yeah.
Yes, sorry,
Yeah.
wrong moon.
Phobos is going in. Deimos is going out.
Deimos is fine.
Yeah.
So it looks like you can also have tidally locked worlds migrate in as well. And so you have collisions that are driving it, you have frictional effects that are driving it. And the newest result that we're looking at is planets have now been found near late type stars that had previously been much bigger red giants.
Yes. I saw
And these
this.
the planets are being found in locations that used to include where the star was.
Right. So we've got stars, we've got planets that were able to withstand their star. They were inside their star for a while.
So they actually figured out how to explain them without having to have them inside the
Oh,
star,
okay.
which seemed like a really bad way to be a planet.
Yeah.
So the way they've figured out how to explain this is you have massive star, and the planets turned out to be in much further out orbits. So the planets weren't actually consumed initially. Star expands out, its rotation rate changes as it expands and contracts. The planets are asymmetric. As the star collapses back down, the same effects that are causing the inner moon of Mars to spiral inwards towards Mars are causing these planets to spiral inwards towards their star. So they were tidally dragged in towards their star as it
Wow.
shrank.
That's really cool. Yeah, and this is brand new.
Yeah.
This is like today, yesterday. So,
Last week.
yeah.
Yeah.
Um so then like let's run the clock back now to think about the early solar system. What did it look like?
It was probably, and here again, this is what we're thinking today. Tomorrow could be different. There is some consensus, but I wouldn't say there's great consensus in our understanding right now. we believe that things started out with all of the outer planets closer into the sun. So our solar system was initially much more compact. The Oort cloud may or may not have been there, the Kuiper belt may or may not have been there, the asteroids may or may not have been there. Over time, gravitational interactions between the most massive worlds in our solar system redistributed everything, leading to the asteroids in the resonant places that they are and they aren't in the asteroid belt, leading to the centaurs grouping up where they are and where they can stay for 1,000 years at a time before they get flung in a new direction, leading toward Uranus and Neptune, perhaps even switching locations
Mm-hmm.
according to some
Yep.
models
And
before
rolling
ending up
Uranus over on its side, although that could have
ex-
happened with a
through an
crash.
impact. And so the best that we can say is everything moved. And we luckily ended up on a world that stayed in the habitable zone for the surface of our world.
Crazy. Um, so then this idea, I mean, how does this help us better explain the other star systems that we see out there in the universe? I mean, as we said, we're now seeing all of this complexity. Why does this knowledge that planets migrate around, how does that help us better understand what we see?
So the two big questions that we're finally able to answer is it's through this planetary migration that we see so many collisions taking place. And if your initial solar nebula is only able to form one fairly significant Jupiter sized world, and then things like Saturn, Neptune, and Uranus, if those Saturn, Neptune, and Uranus type things decide they're going to collide together, this is how you start ending up with these truly massive worlds. So, what we've been finding is truly massive worlds in highly elliptical orbits. And these new models also explain those highly elliptical orbits because that high ellipticity, that's not natural. The easy way for things to form is in nice circular orbits that some resonances can knock things slightly out of the round, but in general, round is how orbits want to be. But when you have collisions and you have separate masses doing it, you end up with a single, much larger object or moons and a central large object, Earth Moon system. And if it happens just right, you end up with the high ellipticity systems that we are seeing.
I mean, I guess when you see a planet like a hot Jupiter and you see this planet that is located really close to the star, that shouldn't be possible. Like it
Right.
shouldn't be there. It couldn't have formed there. Therefore, it had to move there. And the fact that it had to move there means that planets move. Did they move
But
here?
how?
But how?
And
Yeah. And so, what are those? I mean, you talk about the and how. So, what are those mechanisms that are causing those planets to shift around?
so we're looking at three main mechanisms for shifting the worlds around. One is when we still have that young solar nebula with a whole bunch of debris in it, you have an object that forms with a gap outside of it relative to its star and a whole bunch of material internal to it around its star.
Right.
And it starts gobbling up the material inside of it. And this changes its angular momentum and causes it to migrate slowly inwards, depending on how this occurs. And it's through this consumption from the drag and through the conservation of angular momentum that you get this very complex and hard to math out migration inwards in an early solar system.
And I've heard this process might actually happen very rapidly. Like
Yes.
you've got these disks of material, the planet is embedded inside of it, and you've got these tidal tails that are coming from the disk that are feeding into the planet.
Yeah.
And the closest analogies, you can see structures that are kind of like this with the shepherd moons that are orbiting within
Yes.
the rings of Saturn. You can see these lines of material that are coming to these little shepherd moons because of their gravity, and that in fact these movements could have happened in hundreds of thousands of years, the low millions of years at the most. Like, it was not a slow process, it was fast.
Right. So primary planetary formation probably only took a few 100,000 years.
Wow.
And it was during that next billion years that all chaos broke out
Right.
with things moving each other around. And and so you do have this
You mentioned three
frictional
mechanisms, right?
migration. Right. So the next way that we look at things is you have that next phase of the solar systems, the era of heavy bombardment that we saw within our own solar system. This is where you have massive collisions taking place, where you start off with way more worlds than you eventually end up with. And it is through the collision of Earth, Mars, and bigger sized objects that you can grow massive
Right.
Jupiters, you can grow massive terrestrial worlds.
So I kind of imagine this, like, you've got these planets that are on these fast tracks that are
Mm-hmm.
moving around inside this disk of material, but potentially at different speeds. And then you've got planets crashing into each other as they're entering each other's orbits.
And what allows this to take place is as things form, they don't necessarily have the long term stability that they need. They still have all of these resonances that can put them into, on short time scales, much more elliptical orbits that cause these collisions to take place. Now, over time, the orbits do circularize, but even once they're circular, you can still have resonances that slowly move things. And if this slow migration ends up with things in just the wrong or right, depending on your perspective, kind of alignment, you can end up with what we had, which is Jupiter and Saturn going around, such that for every 2 times Jupiter goes around the sun, Saturn goes around once. And gravitationally, anything that hadn't already been flung somewhere is now going to get flung somewhere.
Yeah, and I think you've mentioned in the past that there's still a chance that some of the planets will get thrown out by Jupiter.
And and this is the long term slow effects that we model over the course of thousands and millions of years in our computers, where we can see how the processing of our own Earth's orbit, which isn't a perfect circle, and the precession of all the other not quite circular orbits leads to different alignments over time. We see the Martian pole wandering over time because it doesn't have a giant moon like we have. Very few things are in any permanent kind of an alignment. And I don't think anything in our solar system, except for maybe the sun, and even it is only on like millions of years fairly permanent. Nothing has a permanent alignment because all these slight shifts, all of these slight precessions, can lead to new resonances building up and flinging something hither and yon.
Is that the end of the story? I mean, you talk about, there can still be some interactions, some slight instabilities that build up over time, and Jupiter throws Mercury out of the solar system, for example.
That's not going to happen.
But could there be, I mean, are there more mechanisms in play? Like, as the sun dies and it loses its mass, will we see another round of this?
Yes. So our sun is constantly losing mass, and this means that very gradually over time everything is migrating outwards a little bit. Now, eventually it's going to also expand out as it undergoes a change in the kinds of nuclear burning that are going on in its core, and this change and this massive expansion coupled with the mass loss that is going to predate this, is going to um, eat some of the planets in the solar system, is going to move the other planets in the solar system. And this redistribution will, of course, change what resonances are possible as everything moves. Now, you also have the continued possibility of things like, well, there are 60-kilometer objects in the Centaur belt which are not entirely stable and could get flung in our direction. And that's not necessarily going to change our orbit that much, but who knows what else it could hit along the way and change its orbit.
Right.
And so all sorts of collisions are possible, and you never know when we're going to be affected by another solar system.
So do
We
you
orbit our
think?
Milky Way,
Right.
and
So do you think that we will eventually have a single model? I mean, with things like James Webb, they're going to be able to see newly forming planetary systems and watch those little gaps moving around. Will we end up eventually with some unified model of being able to calculate how planets moved around and where they are likely to end up, and finally know what a planetary system should look like based on all the
well,
factors?
I think what we're eventually going to end up with is a better understanding of all the things that need to go into our computer models and quantum computers and the ability to say, here's all the stuff that can happen, universe go. And then we're going to realize the universe is still finding stuff
Yeah.
we didn't include in our models. I really think that this is going to stay one of those things where the universe remains more creative than we are in all of the diversity that is actually created. There's going to be multiple ways for the same situation to arise. And since humans are short lived, we're always going to have to say, well, here are all the different ways you can get that. And we still may be missing something in our understanding of the universe.
I can't wait for us to discover the weirdness. And we'll make
Yes.
another Weird Issues episode. Pamela, do you have some names for us this week?
I do. As always, our show is supported through the generous contribution of people on Patreon. If you would like to support our show, this is how we pay for our servers, our software, and Susie. Susie being the most important of those three. You can support all of these things by going to patreon.com/astronomycast. This week, we would like to thank Sjartan Svar, Ed, Stephen Shewater, Gordon Dewey, Bill Hamilton, Frank Tippin, George Thorwald, Richard Riviera, Alexis, Thomas Sepstrup, Sylvan Westby, Jeff Collins, John Drake, Arctic Fox, Merrick Videri, Nate Detweiler, James Platt, and Ron Thorson. Thank you.
Thank you, Pamela, and we'll see you next week.
Bye bye, everyone.
Stop. Save. I'm going to save as 546.
I wrote 456. I can fix that.
That was 2 years ago.
It was.
546. Yes.
Okay.
Gordon says maybe our universe is a simulation and we keep finding new things when they apply a patch. Makes sense.
Oh man, that hurts though. It really hurts.
Yep. Arinstro asks, can things like outgassing, the Yorp effect, and so forth contribute to these orbital variations?
Yes.
So, I mean, that's the Yorp. I forget the actual words underlying
the Yorp
it.
is when something has asymmetric coloration and sunlight pushes on it as it rotates and thermally changes.
But that really only counts for smallish mass things. Once
Yeah.
they get heavier, then they can't get pushed around in the same way.
Yes. But for like your half-kilometer sized objects, it's still something you worry about.
Hal McKinney asks, will black holes that don't get added to eventually completely evaporate away whilst retaining their black holiness until it's done, until it's gone. So will black holes that don't, once the age of actively feeding black holes ends and black holes
Right.
run out of material to eat, they will evaporate. Will they
Yes.
still be black holes until the very last particle?
Yes. I wouldn't say the very last particle. Things kind of go crazy at the very end, but
Right.
yes.
So you say kind of crazy. What does that mean?
Uh, as I don't remember the details.
So as I understand,
I
the
I
temperature, like when you see a black hole, when you're seeing evaporation, you're seeing individual particles, you're seeing
right.
photons. And as the black hole's mass gets lower, the temperature of that, the wavelength gets shorter on the photons that you're seeing emanating from the black hole. And when the black hole is like the mass of, I forget, like the moon, it's bordering on room temperature. And as the
Yeah.
black hole gets the mass of a house, it's in the X-rays. And then the last little bit is just this burst of gamma radiation, and then the black hole is gone.
Yes. I don't remember the why of that though, and that's now going to bother me for the rest of the day.
Why do black holes evaporate?
No, no, no. I know why they evaporate. I don't
Okay.
remember why the temperature changes.
Oh, well, yeah. I don't remember either. That's funny. We'll move on. But
It's a lot to remember.
yeah, I mean it's funny because we did I did a question show and someone said like, is there any way to kill a black hole? And the only way that we could come up with was put it in a freezer and encourage begin the evaporation. So if you don't put a black hole in a shielded freezer, then it's going to absorb photons from around the universe and it's going to continue to grow. It's only when
Yes.
there's nothing else to eat that it starts to actually evaporate.
The dog behind me just let off a disgusted sigh at the fact that I couldn't remember this fact.
Yeah. Yeah, I'm sure that'll happen next week. Um, Ponder asks, do you think that we'll ever know everything about the universe, and wouldn't that be boring?
We won't, and it would be boring.
Is there like a mathematical proof to know that we will never know everything? Because like
Well,
I understand that there are places, like when you think about, say, the uncertainty principle, right? There are
mhm,
places where you can't know the position and the momentum of
right,
a photon, for example.
right.
And it's not just because there's a limit to your ability to measure it, but it is literally part of the laws of physics.
Yeah.
So,
Now, beyond that, you also have so much of the universe that we're simply not able to see. And we can only see a snapshot in time. So there's always going to be multiple paths backwards and forwards and things behind the curtain.
right. And so, but will there be like again there's this idea of cosmic variance, right? There is this limit to what we can see in the cosmic microwave background radiation, and the Planck telescope was pretty close to what is, to how accurately you can measure the temperature of the background of the universe, and you actually can't go mathematically any better than that. And so, I mean, it's obviously not realistic for us to attempt to try to measure everything ever,
Right.
but I wonder if there is like, these are the things that are knowable and those are the things that are unknowable, and we will reach some point where all of the knowable things are known and all the unknowable things are forever unknown.
That is conceivably possible with lots of telescopes.
With oh yeah, yeah. I mean, a telescope everywhere examining every cubic meter of space for every
So like
single particle that's popping into and
my
out of existence, right? Or
my current fantasy is to have northern and southern hemisphere versions of Alma that are dedicated to nothing more than surveying the entire sky over and over and over, building an ever deeper map in the millimeter.
mm-hmm. Yes,
I
please.
want to I want to replicate the first survey, but with with Alma and the whole darn sky.
Right. Yes, please. And I mean, we're going to see more of that. When we look at, like, say, the Large Synoptic Survey Telescope, which is doing a better version
Optical.
in optical. No, I understand, but in
Yeah.
optical, it is attempting to image the entire night sky every 3 days.
Yeah.
So imagine, what if you had a telescope in optical, one in infrared, one in millimeter, one in ultraviolet, pointing at every part of the sky at all times, always building up an image of the night sky. I mean, what would that tell us? Be right? It would be the
Yeah.
difference between seeing a snapshot of the sky every 3 days, right? And seeing it in real time, the whole thing, all sky at high
Yeah.
resolution.
Yeah.
That would be
We
great.
just don't have the technology right now.
Or the will. I mean, I think that you could theoretically build a.
Well, we don't actually have the data management tools.
Yes.
Like Cisco Systems is still trying to innovate whatever the heck is going to be needed in order to manage
Right.
LSST.
To dump a terabyte or an exabyte of data onto the internet
Yeah.
every couple of days.
Every couple of hours.
Yeah.
They're looking at like a petabyte a night, I think.
Oh, yeah.
Yeah.
Uh, AbQ Halsey asks, how thick of a layer of air do you need to protect against space radiation? Like if you built a dome on the moon made of thin, self-healing plastic. How good of a protection against
Uh
radiation is air?
uh so I mean like our atmosphere with all of its different layers and all 300 some odd, well it's more like 60 miles of it, um is able to like block out x-rays, block out gamma rays, but
Not
it's
so much
going to
cosmic
take
rays.
miles and miles, and yeah, and you have to have a magnetic field to deal with
Right.
the highest energy stuff. So while you can prevent yourself from getting x-rayed and gamma rayed to death, you're still going to get alpha beta, well, so alpha particles will get deterred by a thin layer of plastic. Beta particles I think will, but gamma rays sure won't.
Mm-hmm, mm-hmm. Yeah, I mean, for like full
And
on cosmic
cosmic
rays,
rays
yeah,
are like,
yeah, go through whatever you got. Yeah.
yeah,
Yeah. And so really you need a lot of
a magnetic
protons.
field.
Well, ideally a magnetic field, yes, or a lot of protons. So instead of air, you need metal or water.
So I want to thank whoever just triggered the bit raid over on Twitch, and also thank um, everyone over on Twitch for being there, watching, and give Professor Milko, Prof. Milko, a shout out for the support over on Twitch.
What's a bit raid?
It's it. You need to get with the
Uh,
times, Fraser.
Get off my lawn. What's a bit raid?
It's where people start showering you with bits and good things
Oh,
occur.
wonderful. So people give
Yes.
donations too. Nice. Thanks, bit raiders.
Oh, it was a big raid, not a bit raid.
Oh, a
So
big
a
raid.
big raid is when a whole bunch of humans invade. So
Right.
thank you, Professor Milko, for coming in with all your
So
humans.
somebody wrapped up a stream and then directed their stream at some other location. In this case, it was us.
Yes.
See, I can learn. I can learn. The Gem Doctor on Twitch says, what could possibly be worth $50,000 per gram that could be mined?
Helium.
No. Like from space.
Someday.
Someday, yeah. Oh. But from space, like what is a really valuable mineral or metal that we could gather up in space to maybe make the whole
Um.
process worth it?
Oh man, I was reading the other day about stuff that was like way more valuable than gold. Um.
Iridium.
Yeah, iridium, basically any of the rare minerals that go into making things like iPhones. And basically your cell phone is filled with rare earth minerals that pretty much only come out of parts of the planet where we don't necessarily have good political agreements,
Right.
and are quite rare, and in some cases were brought to our planet strictly through asteroid attacks. And so these rare earth elements may become less rare if we decide to yank them out of asteroids instead. But then we're going to want to do all of our manufacturing in space. So let's put that next iPhone factory.
Yeah, in space.
Yeah.
Yeah, it's interesting. I think it's Lockheed Martin put a price on water. If you can deliver them water in space, they'll pay you $3,000 a kilogram. So
Okay.
yeah, so bring water from an asteroid, and they'll pay you. Therion says, "Why are most comets so small? Why don't we see comets in the range of tens of kilometers?"
We do occasionally, but the overall distribution of stuff in space is you have more tiny things and smaller big things. Since there's fewer big things, we see them much more rarely, which is good because they're much more destructive. So that comet that we mentioned in the last episode, um, I lost its name, Stellarman Vachman, I think,
Mm,
that is out. That's an active centaur. It's 60 kilometers across and will eventually be a comet. So they're there. They're just fewer by number, and so
yeah.
we don't see them as often.
I mean, this was, of course, Dr. Neil deGrasse Tyson's favorite joke was that Pluto, if you brought it into the inner solar system, would grow a tail and be a comet. So,
And I'm pretty sure he stole that from Mario Livio,
oh,
who,
did he? Sure.
yeah,
So we do see comets that are in the tens of kilometers across. They are called Kuiper Belt objects, and they remain out there orbiting the
yeah,
sun far away,
yeah,
while the asteroids are
exactly.
out there orbiting the sun more closely. But I mean, sometimes those bigger objects will make their way into the inner solar system, and yikes, that would be awesome to see a dwarf planet go around the sun, but it would also be a little terrifying if you happen to be
Yes,
anywhere near its path.
yes, that starts to become a science fiction story.
Yeah. One last question. DPI 209 says Earth has a Trojan as well. Does that mean that we have our own private asteroid belt?
So the definition of these Trojan objects are things that are in the gravitational sweet spots in front and behind the Earth in its orbit around the sun. Um, and that does not a belt make. Belts go all the way around. So you can say that the Earth has a belt of geosynchronous satellites that are studying our weather.
Right.
You can say that the sun has an asteroid belt and a Kuiper belt that go all the way around, but Jupiter has an asteroid belt's worth of Trojan asteroids, and Earth has Trojan asteroids.
Right. I think we know of one.
Yeah, I
I
think
think
so
there's
too.
one known object that's trapped in Earth's Trojan field, and that's fairly new. They only found out about it, I think, as part of the NEOWISE survey. And there's always been this.
Yeah.
They've always known about dust, and it's. I mean, it relates to the size. So the size of the objects that can be trapped in these Trojan regions is dependent on the planet. And so Jupiter can have gigantic ones while Earth has relatively tiny ones. But they are there, but
And
not in the same
they
scale.
thought temporarily that Earth had a small second moon, and then it turned out to be, I want to say that it was a piece of the Apollo debris, a
Well, there's
stage from one of the Apollo rockets.
that's one, but there was another one called Cruina, which was thought to be a fairly small, just a couple of meters across moon,
Okay.
but it actually orbits in a weird horseshoe shaped
Right.
co-orbital path. So it actually dances with Earth on a regular basis, but it
Yeah,
doesn't actually
it's
orbit around the Earth.
slightly more elliptical and
Yeah,
synced up. So with the resonance,
right.
it's more like the pattern made by a bicycle tire on the ground.
But it does look like the Earth gains moons and then loses them again on a fairly
Right.
regular basis.
Which is cool.
But your definition of a moon then has to be something a rock that is a meter across or 2 meters
Yeah.
across, and so it falls into the Earth's gravity well, spends a couple of cycles with us, and then gets kicked back out again. So
Yeah.
come on, it's not another moon. So no, Earth does not have another moon. All right. Well, I think I've decided to call it now at 1:30.
Yes.
So I think we better run. But thanks everybody for joining us today. That was super fun. Uh, Sorry about the network on Friday. That sucked, but we're back. We
Yeah.
did it. So
We did.
time to upload. As someone's mentioning in the chat, I'm not doing an open space because I've got another commitment that I've got to do tonight. But I will be back next week with another open space. And I think we've got a pretty cool guest on the weekly space hangout this week. So stick around for Wednesday for that.
Sounds good.
And no Astronomy Cast on Friday.
Right. No Astronomy Cast on Friday.
All right. We will see all of you next Friday.
Yes.
Okay. Thanks, everybody. Thanks, Pamela.
Bye-bye.
See you next week. Next week. The end of next week.